Okay, I think the record is now on. Okay, you see, from what we did in the first hour, like this is kind of a hardship to try to create the influence line by, you know, solving the free body diagram one by one, placing your unit load painfully at each location. So in, you know, not so long ago, just look at the year, man, 1886, Professor Heinrich Muller-Breslau gave the principle: if a function at a point on a beam, the function that we talk about is the functions that we have done in the first hour, such as a reaction, shear, or moment, is allowed to act without restraint. Act without restraint. The deflected shape of the beam represents the deflected shape of the beam. So let me try to underline that. Deflected shape of the beam represents the shape of the influence line of the design function. So now, if you have proper imagination, you can remove the restraint of your design function, but the force is still there, so it's going to move the structure. So if you can imagine how your beam is going to deform under such circumstances, you can obtain the shape of the influence line very easily. And when we talk about the shape, we call that this word: qualitative influence line. We will know the shape, but not the magnitude. The shape and the magnitude is called quantitative with magnitude. Qualitative here, just the shape. Okay. And, you know, remember, before we start looking at how to exploit his principle, how to use his principle, remember that you can always construct the influence line by placing the load and solve your free body diagram. Keep that in mind, because after I show you this, almost no one will try to solve it by using free body diagram at all. And sometimes your imagination is not very bright and you can't imagine how your structure will deform when you allow these design functions to move without restraint. Okay? So now, knowing this, we are going to go back here, and we have do we have another one? Okay, no, we are going to go back here and look at this beam. We're now going to look at this beam, and we will allow RA to move freely. Okay, so let's say this is our beam. RA is there. What did he mean by allowing RA to move freely? RA is the force in the vertical direction, correct? So when you want your RA to move freely, generally that would mean you would let go the restraint of RA. And the way you let it go, it means that you have a roller in this direction now. Right? Now RA is still there, but you allow it to move freely, and RA will move vertically, correct? RA can move vertically, well, of course, because RA is the vertical force. So RA will move in the vertical direction. And we allow it to move freely by simply adding the roller in that particular direction. All right. Now it's gone again. My wife's trying to fix this, but no, doesn't work. Okay. So hope you guys can still see this, right? Okay. All right. Now, how it is going to move? RA will push this up, right? RA will push this up. Now it is free to move. So your beam will move up like that. See? And that becomes the shape of your influence line. See, it is pretty similar. It is, right? Now, likewise, now I will let RB move freely. And you can imagine that I will add the roller in the vertical direction like this, okay? And RB, which is also a vertical force, will now move freely upward. So your beam is going to go like that again. See, so that becomes the shape of the influence line of RB, which again, incidentally, looks similar to this. Okay, now that is some kind of a shortcut. If you can imagine properly, you see how you will never go back to, using the free diagram to calculate the magnitude of the force and plot. But it gets tricky. Let's say now I want the shape of the shear. At midspan. Okay, how do I allow the shear to move freely? Remember, your shear is positive shear is like this, right? So I will have to now add the roller on both sides, right? Nice. Try to put the wheels in the same location, maybe. Okay, that is your positive shear, right? On the right, on the left is up, on the right is down, on the left is up, on the right is down, on the left is up, on the right is down. So now if I let this go, my beam, because that is down, so it's just gonna have to go down like that. On the left, and it will just go up like that on the right. So that becomes the shape, the shape of the influence line of the shear force at midspan. Okay, are you still with me?
Yes.
Okay, let's try another one. Okay, let me go back and point this to you that, oops, don't have to go that far. You see, this is similar to that. Okay, so we are left with the moment. Okay, the sign convention of the moment, positive, right? How do we allow moment to move without restraint? We apply the hinge, right? So here we go. At midspan, I just add the hinge. And I will allow moment to move freely. Oops, sorry, it's supposed to be the green one, right? Yeah. So here is a positive moment. And if that's going clockwise, this has to be counterclockwise. On the right, you do, and on the left, it's clockwise. So that's positive moment. So when there's a hinge and you rotate the hinge, it's just gonna go like that, right? It has to move up. Imagining the hinge on your door, okay? Right. Doesn't look as beautiful as I expected, but because now I've had cases falling apart again, so I have to draw it in the flat position. So that's a shape. See? Which incidentally is similar to that. Now we have the shape. We can use our proper structural analysis knowledge to help solve the magnitude. Okay, for example, you now know the shape of the influence line is going to be like this. The magnitude that you can calculate, you can obtain right away is by placing the unit load at the support, right? And when the unit load is at the support, you know RA is going to be equal to 1. So there you go. You now know, sorry, you now know the magnitude. And here, when you place the unit load there, you know the magnitude here is going to be equal to 1. So that becomes your influence line. And likewise for RB, there you place the unit load at B, you know the RB is going to be equal to 1. So you know, oops, sorry, that is the magnitude. And because this is the determinate structure, when you allow your restraint to move freely, the deformed or deflected shape of your structure becomes a straight line. Okay? Now, here, you can say, well, you can place the unit load at midspan and calculate the shear. You know the magnitude is 0.5 and 0.5. Or you can just look at the ratio because this is midspan and it has to have the same slope, you know. So you split it in half and becomes 0.5. Here is tricky with the moment. Generally, many students will not have no idea how to do this. And then of course, when you see you can have a shortcut like this, you generally abandon your free body diagram. So the best way to calculate the magnitude here is at here. At this is the value or the magnitude of the moment at midspan when the load is at midspan. Am I correct? That's the meaning of the influence line. So you can, in order to obtain this value, you can just apply the unit load at midspan and calculate that magnitude. And M at midspan for this is, you should know by now, it's PL over 4. That's a formula. So it becomes P is now 1, L is L over 4. So that's 0.25 L, right? Which is the magnitude that we obtain from this free body diagram, right here and right there. Okay, pretty easy, right? So Professor Muller-Breslau were good to us, right? Was good to us. Any question? Hello, are you still with me? Yes. Okay. Any question? Maybe perhaps wanted me to repeat any part?
I have a question ค่ะ
Please
Why
find.
you need to put a roller on midspan or on the reaction at RA?
Because we try to make use of the principle given to us by Professor Muller-Breslau. Okay, he says here. This is the key word, lady. The function allowed to act without restraint. So let us go back here. To act without restraint, what does it mean? This is your reaction, right? If you have the reaction in the vertical direction, it means that the reaction itself prevents any movement in its direction. So do you agree with me on this one?
Yes.
Okay. So whenever you have the reaction, it means that you will not have the movement in that direction. By that, I mean the direction of the reaction. So if we are going to allow the reaction to move without restraint, the word prevents any movement in its direction. It means that this is the meaning of the word restraint. Okay. So when I want to remove the restraint of the reaction, it means that I will allow the reaction to move in its direction. And the only way that I can allow the reaction to move in its direction is just by adding a roller. And when we have a roller, now you can free to sort of which color should I use? You're free to sketch up and down, correct? So
Yes.
by roller, we now free the reaction from the restraint. And when the reaction is free from restraint, it means it is free to move. So the reaction itself is going upward. So it is now free to push the beam upward, thereby giving us the approximate shape of the influence line.
Okay, I got it. Thank you.
Good. Okay. What else? Is there any more question? And for the shear, the reaction is like one way, but for the shear, this is the general idea of the shear, right? We have shear on both sides, so we need to free that on both sides. So we put two rollers on. And the restraint of the moment is that it prevents rotation. So when we want to free the moment, we add the hinge.
Can you repeat how to apply the magnitude to the shape for the midspan again?
Which one? The shear or moment?
The shear.
Okay, the shear, there are actually, if you know the shape, you can, start by, applying the force as usual like this. That's the first one. To try to calculate what the shear is. Or because, this has to go up and it has to go down. And, sorry, I should draw the new picture, right? Now you know the shape and you apply the load here, okay? This load is 1, right? So the change of the shear underneath the load itself has to be equal to 1. Am I correct?
Yes.
Yeah, because the shear force diagram, let's say, oh, no, not there. Try to put things in order, okay? Shear force diagram of this is essentially this, right? This is shear force diagram, okay? And shear force diagram generally represents the magnitude of the load. So that is 1, correct?
Yes.
You have the unit load here. The unit load is equal to 1, of course. The change of the shear when you're on the left and on the right has to be equal to the load itself, 1 that is, correct?
Yes.
From the shape, now you know your shape is like this. Your shape is like this. So you know this height has to be equal to 1. right?
Yes.
And the only way, because this is midspan and the length on the left is equal to the length on the right, the only way for you to have the magnitude in the middle equal to 1 is that you have to split this 0.5 up and 0.5 down. Okay?
Okay ครับ
You can just, you know, go the old school way, cut the free body diagram, apply the unit load, calculate the reaction 0.5, and then cut the free body diagram. You get it. Left and right of the unit load itself. And for the moment, we have no direct way but to apply the load itself at this location where it is most convenient to calculate the moment. And for me, it is midspan. So I apply the unit load at midspan and calculate the moment at midspan right away. Doing this with this formula, I now obtain the value at this point, which is 0.25 L coming from this. Now I know the magnitude, I know the shape, that's it, it's over.
Okay ครับ thank you teacher
Remember that this has no relationship with the magnitude of the load directly. You have to calculate the moment. Remember that this is moment. Okay?
Okay ครับ
I like all your questions. So do keep your participation up. Okay? Do not be afraid to ask any questions thinking, hey, some of my friends already know the answer. The most important thing is that you don't. So you need to ask. So if anybody already knows the answer, just let them be. Okay? You don't need to care about them. Okay? So if we say we think we understand the concept, so let us try to extend the understanding by trying to solve this guy. Okay? Now, we are going to draw the influence line of RB, RD, VA, VB, to right, VC, MA, MB, and MC of this beam a lot, right? But this time we are equipped with the Muller-Breslau principles, and hopefully we can take care of it. And this problem will demonstrate why I love the influence line. If you can see the influence line, it means you know how the design functions of your beam will change when you place the load on each location. It means that you are beginning to talk to the structure, really. Okay? So let us begin with RB, shall we? RB, that's your beam. So let us draw the beam here. Is it okay if I don't draw the thickness, or you want me to draw the thickness?
it's okay
Okay, right. So let's say that's our beam. Thank you. Here is the roller at B. Here is the hinge at D. Now, yeah, the reaction is there as usual. RB. Now I want my RB to move freely. It means that RB can now push the beam up like this. Right? Not very straight. Yeah, you try to. Yeah, you guys okay with that? Okay, right? So that becomes the shape of the influence line of RB. But wait a minute, we need the magnitude, right? So how do we obtain this? In the easiest way, we again place the unit load at B. When we place the unit load at B, we know RB is going to be equal to 1, right? When the unit load is over B. So from that, you now know that, hey, here RB is equal to 1. So that becomes my influence line of RB. Okay. Here, the magnitude is 1. So what is this? We can just use the similar triangle to finish the job, right? If that is 1, this is 4, the entire length is 6, so that is 1.5. The question, that is the influence line of RB. You know what does this say? Says that when you apply the unit load here, you know the seesaw effect, right? When the unit load is over there, RB will have to be greater than the load itself. And RD will become the downward reaction, which you will see. So when you place the unit load here, RB would have to be greater than 1. And we have 1.5. If you don't believe me, you can take moment at D and see it for yourself that RB will be equal to 1.5 because essentially is now 1 multiplied by 6 over 4, right? RB. Any question? So that is the influence line of reaction at B. Very, very easily by Muller-Breslau. Let me remove this. Any question on this? Hello, you guys okay?
I think I don't have any question.
Okay, good. Thank you for telling me. So let us move on to RD now. Again, the beam is as before. We have the roller here as usual, and we have the hinge. Out on the scale. Now we are trying to remove the restraint of RD. So RD is now free to push your beam up, right? So it goes up like this. But here we have restraint. So it has to go up like this and go down like that, right? It's like, imagining, okay, if we push this, how is our structure going to move, right? So we push at D, D goes up, RD goes up, and we still have the hinge here of sort that goes up, comes down. And again, the easiest way to obtain RD is by applying the unit load here. Now you know RD is equal to 1 when the unit load is right on top of D itself. So with that, we know the magnitude here is 1. And I can easily write my influence line of RD now. It's going to look something like that. That is 1. Okay. So let me move this here a little bit. Okay. This is the influence line of D. And again, we can use similar triangle. If you see that this is 4 and 1, this is 2, so this is, what do you think? Minus 0.5. Right? Similar triangle. And like I said before, that when we have the unit load here, 1, you would expect RB to be greater than 1, right? And now RD would have to be the downward reaction. And we have it here, minus 0.5. And when you have the unit load here, okay? You still following me? When you have the unit load here, your reaction here is 1.5, here is minus 0.5. Let's take a look at sigma Fy itself. This plus that is 1, equal to this in the opposite direction. So our sigma Fy is equal to 0, right? Every time. When my unit load moves to be, my RB is now 1 and my RD is 0. So sigma Fy is correct. And again, when I move this here, now my RB is 0 and my RD is 1. So sigma Fy must always be correct as well. Any question? Now the fun part will begin with the shear. Okay, no question. It's all quiet. So without further ado, I am going to start looking at VA, right? This is going to be fun. Okay. Same beam. I will let VA move freely by adding a roller here, right? Oops. So imagine that. What's going to happen now? Let's use the pink, okay? The shear is like that, positive. So on the left piece, the positive shear is like this, right? So the left piece will have the downward shear on the right, and it has a roller. So it means that this piece will fall down indefinitely, right? The piece on the left just fall down because now you allow this right shear to move freely. So this piece has the shear on it, and there's a roller there, so it's just gonna go down just like an elevator. Correct? Let me try to okay, draw this. But on the left, you have this and that. On the left, I mean on the right, I'm sorry. On the right, okay, your shear on the right is on the right piece, this one, the positive shear is up and down like this. So you have this guy going up. But now you have the upward force trying to move this beam, trying to move it up, not trying to bend it. It tries to move this up, but this particular free body diagram has two vertical restraints, so it doesn't move. It can't move. While on the left, you have the downward shear here with the sort of a free end with no support at all. So this guy is so free to move anywhere in the universe. So now that means the shape of the influence line of the VA is just this guy just going to come down like this, right? This piece coming down. So the shape of the influence line is just this. That's the influence line of VA. All right, so how's your imagination now? And now you know the shape, of course, the magnitude will be easy because it has to be -1. So now imagine this, ladies and gentlemen. If you have a beam, this one, and you focus on the shear at this location. Okay, let me go back to this one. If you focus on the shear at this location, the only way that you can have the shear acting at A is by having the unit load here on the left side of A. Because when the unit load is on the left side of A, it can tear this portion off from the beam. So it means that at point A, we now have the shear. But when the unit load moves to the right of A, can this load shear point A off from the beam?
No.
No. So that means when the load is on the right side of A has no shear because there's no load acting on it. This unit load, when it is right here, it will be absorbed entirely by this portion of the structure. In here, it doesn't have anything to do with the load anymore, and A is free from any load. So the shear at A will become zero as soon as this moving load moves past point A itself, and hence our influence line. It looks like that. So you see, a Muller-Breslau works, and we can explain the behavior of our beam in engineering terms as well. Any question? See, if you look at this from an engineering point of view, you see, you look at the beam. And if you understand this, when we place the load here, this load is now capable of tearing point A apart from your beam. Correct? It can still do the damage, and the damage which is equal to the load itself, because as long as the load it stays around here, there is nothing to carry except at point A. You mean when we focus at point A, there is nothing to help carry the load. So the load here is fully acting on point A. But as soon as the load passes point A, this load will be carried by the structure, to the right side of A. And A is now free of any stress because the load is no longer there. So it is also free from shear. This is the understanding of how the load will affect your design function. That is the beauty of influence line, if you ask me. Okay? Any question? Hello?
No.
Still good?
Yes, still good.
Still good, good, because the next one will be more fun. Oops.
Still pain.
All right, all right. Oh no. Next one is VB to the right of the support B. Before I go into that, let us look at the B. When you look at the shear force diagram, okay, now we are back at the shear force diagram of a point load. Let's say I apply the unit load here. Now let me use another page. I don't want it to be here. Stupid thing. No, I don't want this here. Can I crash it? Okay, I want it to be here. Okay, we have space here, so I can use it. Let us look at this beam. Let's say if I apply the unit load here, or whatever the load is, and this is my beam. and I draw the shear force diagram. Okay. The shear force diagram of your beam would look like this, correct? Am I correct?
Yes.
The shear force diagram, right? So from this shear force diagram, what you should be able to tell is that when you focus at B, you have two values of the shear, right? Why is that? Can anyone tell me? Now this is like a putting your,
Cause
Yes.
the shear on the at the left side, like little or to the left side is negative, but the right is already positive.
yeah, it's a good answer, but it doesn't really, you know, hit the bullseye, you know, but you're right. When we look at the shear here, you know, you have the reaction here, right? Correct?
Yes.
Whenever you have the point load, what the point load does to your structure is that it causes the abrupt change of shear at that particular location. Just like this. Let's say a simple structure, and I apply the force. The shear force diagram here is this. So you would have two values of the shear depending on where you are. Just like we discussed before, because this unit load causes the abrupt change of the shear. That's why you have the sharp, say, drop of the shear force diagram. Whenever you see the point load, your shear force diagram will always have to have a sudden drop or sudden change of value because of the presence of the load itself. And right here, you have the reaction. And the reaction itself is a point load. Am I right? So the reaction itself will cause the sudden change of the shear force. Meaning, when you look closely, the shear force right under any point load will always have the value on both sides. Because now, if I draw the free body diagram, before I reach the support, this is my free body diagram, right? Correct? Right?
Yes.
And when I draw the free body diagram, just right after I reach the support, this is a reaction, and then I have the shear force slightly to the right, perhaps downward, right? So it depends on where you stand exactly, slightly to the left of the reaction or slightly to the right. If you stand slightly to the left, this is your free body diagram. If you stand slightly to the right, this becomes your free body diagram. Notice that this is going up to the right, meaning it is a negative shear. This is going down to the right, it's positive shear. So actually, I'm not doing anything new at all. I'm just, you know, say, put the magnifying glass on the free body diagrams and what you've been doing all along. So now when we talk about the VB on the right side of this, we are talking about this free body diagram. We are talking about this free body diagram. Right? Hello? Are you with me?
Yes.
Okay. So this is to the right. This is left. Now you get this picture first. So now when we talk about the influence line of VB to the right of the support, it means that you are now going to have to allow the shear slightly to the right of support B to move freely. Okay, that means we are now going to have this. Here is the support. Here's this. And now I will have this freedom slightly to the right. Okay, so this shear up and down, so on the left side it goes down, on the right it goes up. Okay, so now it's time to use your imagination, because if slightly to the right, we allow the shear to move downward, because it's just slightly to the right of the support, it has the seesaw effect, because this guy got pushed down, so on the left it got pushed up like that. You see that? And now on the right, it has freedom to move up, so it's just going to go up like that. See, let me repeat that again. On the left, now you have this. You allow this downward shear, which is slightly to the right of the support, to move freely downward. So slightly to the right, it moves down. So it pushes this portion on the right down. So on the left, it goes up, because it's just like a seesaw, right? Or maybe I should draw this. Let's exaggerate this a little bit. It goes down slightly to the right. So when this one goes down, it just pushes the left side up. But on the right, it's pretty straightforward. It goes up, so this entire portion moves up. Like that. So that's it. Are you with me? Oh yeah, it's like the fun part just is about to begin now. So the shape of the influence line will be like this. Like that. It should share again, should share the same slope. So let me try to rectify that. Okay. All right, looks, oh, it looks like straight enough. Okay, whatever. Okay. So this is the influence line of RB to the right. Okay. And again, we can use the ratio when it moves slightly to the right, you know, your unit load is there. So you can use that to obtain the magnitude here equal to 1. And if this is 1 based on the 4, this is 2, so it becomes 0.5. Okay. Any question? Hello?
Can you repeat the last the last that you draw again
Which one?
below the influence line?
The entire process?
Yeah.
Okay, fine. All right. So should I erase this so that you can get the no, let's move on to the to the new space, and let's repeat this, but I'll try to make it bigger this time. Okay, here is our structure. Now we are interested in the shear slightly to the right of this roller, okay, which is right here, slightly to the right. So our section here actually is pretty much like on B, but as I have demonstrated, explained before, that we need to we will have two values of the shear wherever we have the point load, and the reaction is a point load. So we need to consider both sides of the load. Now our focus is slightly to the right side of the reaction. Okay, so now when we are slightly to the right side of the reaction, if I am going to draw this even bigger, oops, damn it. Okay, let's put the thickness on it. And if I am going to allow this to move freely, okay, now our sign convention for the positive shear is this, right? So on the right is down, so this guy is now free to move down. But because they are slightly to the right, so this will go down like this. On the right, and thereby pushing the left side up. Because we are just a tiny bit to the right side of the support. That's why we have this kind of shape. Okay. And for the part on the right, okay, now the shear is on the left, it goes up, positive. On the right, I think it's pretty straightforward because there is nothing, so it's just gonna go up. Oops, like that. This gets in the way. Okay. It looks pretty ugly a little bit. Okay. Now, but when you look at the value now, on the right will help you, because here, when you apply the unit load slightly to the right, this has to be equal to 1, right? So now you know the magnitude. This has to be 1. And they're supposed to share the same slope. This is 1/4 meters. This is 2 meters. That's why here is 0.5. Okay, does that help now with the thickness?
Yes, thank you,ค่ะ.
Okay, good that you asked. So you see, now we have incredibly like two triangles lined up together. In the end, that's why this becomes our shape here. Okay. All right, see, actually you can obtain this by using your free body diagram, you know, but you will not do it because my imagination is good. Muller-Breslau is quick, pain-free. But if you don't really see how, you know, things move, or how the load actually changes when you move the moving load around, your imagination will lead you to, you know, the wrong place. Okay, so any more question? Folks? Hello?
Crystal clear.
Hopefully, right?
Hopefully.
Okay, so let us take a 15-minute break now. You need a longer break to clear your mind so that it becomes crystal clear again. And we will finish this problem in the last session for today. Thank you for your attention. Okay.